So step 1, step 2 time, where this is basically just the reaction coordinate diagram for the previous reaction. This first hill represents going from the reactants on step 1 to the products in step 1. So these are the products of step 1 plus any new reactants from step 2. Then we go over a second hill to form the products of the reaction. Keep in mind that transition state and intermediates, those are different. So transition states, they're very difficult to predict geometries with those. The transition state is found at the top of a hill. So there's going to be a transition state here and a transition state here. The intermediates are going to be a product, so it's an actual thing that we can isolate. Possibly. All right. Questions on this? Yes?
Is there any significance to the slope of the energy and reaction graph, or is it just the peaks?
Yeah, there's no real significance to the slope here. It's just sort of it's just how we draw it. They're working on something out there. It's like, if you ever walk in this hall, it's like 900 degrees no matter what time of year it is. I think there's some heating out there. It's disgusting. Anyway, okay. It's really hot. Also creepy. Yeah, so you should totally go in there. It's great. Rate determining step for a multi-step mechanism. So in our last example, we had 2 different steps. And for every mechanism, one of the steps is going to be rate determining. It's going to be the slow step in the reaction. And your book uses this example where you have you're trying to get from point 1 to point 3 in a car. And there's toll plazas, okay? So each toll plaza is going to represent an activation energy. So in our first step, we're going to go from point 1 to point 2. And if the rate determining step is maybe the gates at the toll plaza A aren't working properly, so it's really slow through there. If that's the rate determining step, things are going to get backed up at 1. Okay? In the second figure here, what this is saying is that if step 2 were the rate determining step, getting from point 2 to point 3 would be slow, and you would get back up at toll plaza 2B, whatever. So this is your 2-step, point 1 to point 2, point 2 to point 3. I like thinking about the rate determining step as what would happen in a relay race. So I'm a very slow runner. I've been told on a couple occasions that I look like I'm running with a refrigerator on my back. Kind of funny. Anyway, so if I were running a relay race, I would most certainly be, hopefully, the slowest person. And so I would be the rate determining step. Me going from my starting position to my ending position, that's going to be rate determining. Okay, all the other people will be fastest. The rate of us completing the race will be based on my slowness. Okay. Yes?
So for the second intermediate steps, where the slowest step, during the experiment, would we see the intermediate around longer during?
Yes. So possibly. We're going to look at the case where we're going to have a fast first step and a slow second step. The products of that fast first step may be around longer than if it was a slow first step. The slow first step for sure, those will be, no, not for sure. For the slow first step, those will get consumed very quickly. I say maybe because what we're going to see is that there's an equilibrium with the products of a first step, if the first step is fast. And so it may shift back to reactants very quickly. But let's first look at a mechanism with a slow initial step. So let's say this is an elementary reaction. where we have NO2 plus CO forming NO and CO2. We might have looked at this before. Because we're saying that this is an elementary reaction. Oh, no. I'm sorry. Sorry. Take that back. Not an elementary reaction. Okay, we're looking at this reaction. This is an overall reaction. Sorry, I should probably look at my notes sometimes. And experimentally, we determined that the overall, that the rate law is this. Rate equals K times NO2 squared. So we know this isn't an elementary reaction because if it was an elementary reaction, the rate law would be the same as, would be derived from that, but it's not. Okay, sorry, hope that wasn't too confusing. Are we good? Okay. So we're saying that this is our experimental rate law. Rate equals K times NO2 squared. And that the proposed mechanism is a two-step process. Where in the first step we have NO2 plus NO2 forming products. And then that's our slow step. And then in step 2 we have our product, NO3, reacting with CO to form NO2 and CO2. And that's a fast step. So what would be the rate law for the rate limiting step? In this type of instance, the rate law is based on what you would predict based on the slow step. So the rate law for the slow step predicts the rate. Now I'm just looking at this step 1, rate equals K times NO2 times NO2, or NO2 squared. Okay. So when you go about these problems, you may not know what the experimentally determined rate law is, but you may have a problem where it says determine a rate law based on just step 1, step 2, and which one's fast and which one's slow. Okay? So the second step doesn't affect the rate law because it's occurring so much faster. Okay? So the rate law is going to be what's controlling the rate of a reaction? And if you have a really fast step in comparison to a slow step, that really fast step doesn't really matter. Okay? It's the slow step that's going to play the bulk of the role in determining the rate law. Does that make sense? Yeah.
So those steps, are they, do we have to calculate them or derive them or anything, or are they actually given?
No, so the steps will be given. Usually, so in real life, this is a proposed mechanism based on some experimental details. For what you're going to see problems where it says this is a proposed mechanism, step 1, step 2, step 3 if there is one. What's the rate law? Okay. So here's another example. I'm going to let you all try this. So we have the decomposition of hydrogen peroxide, and is thought to occur through a two-step mechanism. You have a slow first step and a fast second step. So I want you to write the chemical equation for the overall process and then predict the rate law based on the facts that you know. Just take a couple minutes. Feel free to talk to your neighbors.
As a catalyst, do we put it in the chemical equation?
No.
Okay.
And it does get canceled out.
Okay.
Yep.
Okay.
You cancel it out when you're looking at the liquid.
Yes. For the overall reaction, right, it doesn't go in there. Oh, but were you asking about the rate law?
Actually, yeah, it wouldn't go in the rate law, right?
It can, yeah.
Okay.
Yeah. So, yeah, it goes in here. There's also interesting cases with enzymes. So if you take biochem, you'll see that the enzyme catalysts always show up in a rate law because they're just making everything
It has
happen.
to like smash the molecule, right?
Yeah, yeah.
So in this case, like would we actually put it in the rate law?
Yeah, I mean, I would base it off of the slow step. In this
Okay.
case. If if you had maybe a 3-step, first step was still slow. Let's say there's another step up here,
Sure.
and this was the slow step,
Okay.
then maybe that would
If it was like
wouldn't
slow,
show
slow,
up.
fast.
Yeah,
Okay.
or slow, fast, fast.
Okay.
Yeah.
Well, if it's in
Yeah.
Would this be part of the rate law, even though?
Yeah, it's going to show up. Even though it's a catalyst, it's going to be a special situation. Yep. But it does show up. Okay. Ooh. Getting some good questions. So I saw a lot of rate equals K times H2O2 times I minus. And people were asking, does I minus show up? Because it gets canceled out in the overall reaction. I minus in this case is a catalyst, and it can show up in the rate law. So we're going to leave it in there. The rate law is still based on that slow step predicted as such. Questions on that? Yes?
So we don't really need the overall to get the rate law?
Right. You do not need to have the overall reaction to get the rate law. It's just another thing to make sure everything balances out.
So you just take the reactions from the slow step?
Yeah. In this case, when the slow step is the first step, you simply take them and include those in the rate law. Nothing very complicated about that. It is that simple. Yes? So I minus in this case, because it's in the slow step, is included in the rate law. It's a catalyst. It's not an intermediate. So we are going to talk more about catalysts. Catalyst is going to make the reaction occur faster. So even though that's a slow step, this catalyst is going to help the reaction proceed. So catalysts can show up in rate laws. Intermediates cannot. Okay. Other questions? Yeah. How do you know if it's a catalyst or an intermediate? So the catalyst will probably show up on the reactant side first, whereas an intermediate is going to show up on the products first, in the first step, or an early step, and then be consumed later on. So products and then used up as a reactant. Yeah, good question. Other things? Okay. Oh man, it's getting hot here, right? I'm not clear. Okay, it's very warm. All right, I'm going to leave this one to you guys because we only have about 15 minutes before Jennifer will be here to help us with our iPads. She's coming today. I've checked 3 times. Okay, so this is a more fun example. When we have a fast first step and a slow second step. So this is a little harder to predict the rate law, but also more fun if you like algebra. So, oh, I heard a groan. It's good. Okay, so it's important to note, and I briefly talked about this, when we have a fast first step, we can assume that there is an equilibrium in place. And most of the time, you'll see the equilibrium arrows. Okay? So what that means, by definition, at equilibrium, the rate of the forward reaction is going to be equal to the rate of the reverse reaction. Okay. So this is basically the definition of equilibrium. So when A and A combine to produce M, someone was asking about an intermediate, or if you could isolate M, the product of the first step. It will be at the top of it will be able to either go back and form reactants or go on and react in the second step. Okay, so even though we've got this equilibrium, so it'll go either back to reactants or go on and react and form products, or form eventually these products. Any case, the rate for the fast step, holy moly, is warm. In the forward direction, rate equals K1 times A squared. So it's A plus A squared. We also need to know about the reverse reaction. In the reverse, rate equals, I'm going to do it this way, K minus 1. So it's showing that it's a K for the first step, but the minus tells me that it's going in the reverse direction. K minus 1 times M. So in the reverse direction, the products of that step 1 become the reactants. And so it's still an elementary reaction. So we can use that here in place of forward reaction where it was A squared. So why am I doing that? If we were to derive the rate law from the slow step, we would end up with rate equals K2 to signify the second step times B times M. What's wrong with that? What's M? M's an intermediate, right? All right, well, let me do that. Okay, so intermediates can't show up in the rate law. So when you see a reaction mechanism with a fast first step and a slow second step, you're going to find that an intermediate is going to show up in the rate law derived for that slow step. Okay? So there's a workaround for that. And what we're going to do is basically solve for M. Okay. We know that the rate of the forward reaction is equal to the rate of the reverse reaction in equilibrium, which means we can set these two things equal to each other. Okay, so we're going to have K1 times A squared equals K minus 1 times M. And now we have an equation where we can solve for M. And then we can plug that into our rate for the slow step. Okay, so let's solve for M. Oh, I'd already wrote that. So M is going to be equal to K1 divided by K minus 1. I'm just going to leave all my rate constants in a grouping times A squared. So now we can plug this into the rate for the slow step. And we'll find we have the rate equals K2. I'm going to go ahead and substitute in all of this. It's K2 times K1 divided by K minus 1 times A squared. And don't forget, we still have B. Okay. The other thing is because the K values, K1, K minus 1, K2, they're all constants, we can just rename that another constant. So you may need to do this or may not. Sometimes a homework problem will ask you for basically for this. But it's nice to sort of only have one K. So rate equals K times A squared times B. Everyone see how that works? All right, I think we've got one for you to try. I'm going to skip that. So this question gives you a proposed mechanism and then some experimental data and asks you if the data prove that the mechanism is correct. Just wanted to point out that you can't really say prove. You can only prove a rate mechanism is not correct or incorrect, but consistent with is the right verbiage here. Okay. So anyway, let's move on. There's some summary slides. Oh, okay. So that's basically the end of 14.6. There's a couple of extra problems in the slides if you want to work on those. But I do want to talk a little bit about catalysis. So we use catalysts a lot in chemistry, in making reactions occur more quickly. It's really important in making fertilizer. I know that seems like a silly example, but it is really important there, and in various other places. So a catalyst, as we've seen with the iodide example, is something that will make the rate faster, but is not consumed in the reaction. So not consumed. So with the iodide example, we saw that in step 1 it was used up in the reactant as a reactant, and then in step 2 it was produced again as a product. So it wasn't consumed completely in the reaction. You would be able to recover all of that. So there's a couple of ways that catalysts work. Number 1 is sort of like the main way, and that is that it lowers the activation energy for a reaction. So it decreases E sub A. Okay. There's another way your book briefly touches on where a catalyst basically allows for more collisions to take place. One of the ways that this works is, let's say, I think this is actually how catalytic converters work. You have a metal sheet, like platinum, and the reactants combine on that metal sheet and are able to sort of wander across that sheet and come in contact with each other. That's a way of increasing collisions. But the main one that we're going to talk about is lowering the activation energy. The other thing that a catalyst will do is change the reaction mechanism. So here's our uncatalyzed hydrogen peroxide decomposition reaction. And so we have a potential energy or a reaction progress diagram with some amount of activation energy E sub A. All right. For the uncatalyzed example. When we do the catalyzed reaction, the overall E sub A is going to be lower. Now there's multiple steps, but overall activation energy is lowered, and so that allows for the reaction to proceed more quickly. I think so I'm showing the catalyst here as bromide, so iodide would work as a catalyst, bromide would work. That's kind of fun. And then enzymes. So enzymes are just biological catalysts. They're usually very large proteins, and they catalyze very specific reactions. There's a huge number of enzymes. The kinetics associated with those are really interesting. But sort of in general, the way this works is we have an enzyme. This is showing you the lock and key method, or description, sort of the terminology you'll see. Basically, our enzyme is going to allow for the reactants, which we're going to call the substrate, to sort of go into the right place. It's going to hold them there. We call it lock and key because the shapes are sort of such that only those types of reactants will fit. When the enzyme and the reactants combine, it forms the enzyme substrate complex, and then as the reaction proceeds, products are formed. You can see we have a decomposition of some kind where two products are formed, and then those are released from the enzyme. One of the important things is that the products are held less tightly to the enzyme than the reactants are. Okay? So take a look at those in your textbook, those two parts of section 14.7, and read through that. Again, you'll probably see that come back at you. All right, are we ready for iPads? Okay. There we go. I think it's important that we do this next. Okay, so I want you all to work on a rate law for this mechanism. Ooh. Yes.
So, I think we saw this last time. This whole thing just equals K, right?
Yeah.
Okay.
We're just renaming it basically.
All right. Is it because the K1 and K sub or like -1, do they cancel?
They don't.
Okay.
We're just basically saying this is all a constant.
Oh, okay.
So so we're just calling it K.
We're just simplifying.
Yeah, we're just
Okay.
simplifying it.
All right.
Yep. How's it going? Are we sweating up here too? Yes, it's warm. Any questions? Questions up here?
I don't see it. Sorry, I don't see it in the slides here.
Do you have? There might be a new set. I may have not included this on my original set that I posted on Carmen. There should be part 4 edit, I think is what it's called. Sorry about that. You guys doing all right? Shit, man. It's 100 degrees. Wish I had a nicer t-shirt on underneath. I'd be taking this off. Yeah, I thought they're definitely out there working on whatever, pipes and things. Yeah. I know. Brutal. All right, questions back here? How are we doing? Any questions? Questions? Concerns?
So we're supposed to find the rate law, is it like the basic one, or since it's fast, we find like the
Yes,
first ones? 'Cause I did
so,
all three, sorry, I did all three, I guess.
okay, so it's going to be using the technique we did in the last problem, where you have the equilibrium for the fast reaction. You're basically plugging that into what you predict from this because we have an intermediate. Yep, so, yeah. Cool. You guys have questions?
I just have a question. Would this be right for the first or do you not include this?
Yeah, so you do include it. Why do you ask that?
Oh, I'm just like wondering if I'm doing it right.
Okay.
The other one though, have we seen?
Yes, looks good.
And then the
CL2, but yeah.
And then this would just include the NaCl.
Right.
Okay.
Yep. You guys good?
Yeah, I think so.
Okay.
I've been better sick while.
Oh God, great. I'll just keep walking. Any questions over here? Questions? Okay. Any questions, guys? Okay. 5 minutes. All right, I'm seeing a lot of good work. So I'll go ahead and work this out with you all. So based on the slow step, our rate law would be rate equals K times NoCl2 times NO. But NoCl2 is an intermediate, so it can't appear in our rate law. So we need to be able to substitute that out, and we do that using the equilibrium from step 1. So the forward reaction for step 1, the rate law is, rate equals K times NO times Cl2. And the reverse reaction, rate equals K minus 1 times NoCl2. We can set these equal to each other because at equilibrium, these rates are going to be the same. So they're equal to the same value. So we have K1 times NO times Cl2 equals K minus 1 NoCl2. And we'll solve for NoCl2 and then plug that into this rate expression, rate law. So I'll have NoCl2 equals K1 over K minus 1 times NO times Cl2. Plug that in, and I'll get rate equals K, I guess I should have put a 2 here, K2 times K1 over K minus 1 times NO, and I'm going to go ahead and square that. We're going to have NO and NO times Cl2. Questions on that? Yes?
You said we can just substitute the K, like all the K's for just one K, right?
Yeah, so basically what we end up with is that this is just another constant. So K2 times K1 over K minus 1 is a constant. So I just make up another K.
Okay.
Yeah.
So, like on an exam, do you think the location, the little subscripts would show up, or do you think we would just call it K?
It's possible for either. And I know in the homework that sometimes it will ask for what is the K, is it K2, K1, however that is, multiple choice type thing. What's that?
It's just the steps.
Yeah, it basically is just asking you for the steps. But it also may show up like this.
Okay.
Yeah. What else? Yes?
You typically read that thing up from the K1 over K minus 1 with NO to the power of 1 to the next line where it's K2 multiplied by that and put NO to the
here to here? Okay, yeah, so I took this and I plugged that in here. So NoCl2, this is all NoCl2. I plug that in. Mhm. Other questions? All right. Let's go back a little bit then. I've got like 1 minute.